Good morning, everyone. I am Sugavanam from Mahindra Institute of Technology. Today, I am going to present my internship project that is microwoven simulation using PIC16F877A microcontroller. This project was completed as part of my internship at Emertxe Embedded System internship. So, let's start. The introduction. The goal of this project is to build a digital micro-oven controller. It is an event-driven system, meaning it reacts to the user input via keypad and internal timer overflows. We have implemented four major cooking modes, that is micro for manual power and time setting, grill mode for high heat cooking, and convection mode for temperature based baking with preheating. Quick start. This one for one touch 30-second cooking for initial food to to get initial heat, and last one is user interference. 16 into 4 CLCD display for to display the function on what's happening on the micro oven, and 4 into 3 matrix keypad for input. The real-time logic using timer 2 and interrupts for non-blocking the countdown while functioning the micro oven. Output feedback. The output was produced by the fan heating simulation and buzzer for the completion alert. And I proudly say what I learned from Emertxe Institute of Technology, the technical outcomes. During this internship, I gained deep technical insights into embedded C, focusing on memory efficiency and portability. And second one is advanced pointers and null pointer concepts. The modular programming and its functional and file handling, embedded C and preprocessor macros, and I mastered the PIC16F877A architecture, learned how to control hardware registers, and practiced interfacing peripherals like LCD and matrix keypads. I and also gained the knowledge about I/O peripherals interfacing and timers and interval service routine like known as ISR, and I also become a proficient with industry tool like MPLAB, its IDE with and also PICSimLab for simulation. So the first one, microwave oven operational modes and working. This project implements for four distinct cooking operations using this microcontroller, each with its own combinational control logic and its timing. The system initializes the with welcome message and a main menu, waiting for the user input through a matrix keypad. And the micro oven actually waits for the information that is given to it. The modes include micro mode for standard heating, grill mode used for high heat cooking, roasting, and the convection mode as feature the mandatory preheating phase. For immediate cooking, the quick start mode is provided to default to 30-second cycle. All modes utilize timer to interrupts for precision and non-blocking countdowns displayed on the LCD display. The micro modes, as I said, allows manual setting for power and time. It's a manual cooking. Grill mode for user for high heat cooking. The convection mode include the preheat cooking to preheat the initial heat to the food. And quick start. Sorry, the quick start mode is an initial heat provided to the code. The convection mode includes preheating phase. It preheats the oven to when before the food is given to the micro oven, followed by the temperature based baking. The one of the main part of this internship was embedded system that I learned first. Embedded system is a combination of hardware and software designed to do a specific task. A specialized computer system designed to perform a specific dedicated functions with a large mechanical or electrical system. The key characteristics of function. Unlike a PC, it only does one task. Example, a controlling a micro oven. Real-time constraints must respond to inputs like a key in this project. Keypads are the input interference to do a specific task in the micro oven. Resource constrained, the optimized to run with a limited memory like RAM or ROM. random access memory or random access memory or read only memory, and the with a low power consumption. The embedded system. The microwave controller is a perfect example for an embedded system where the software is tightly coupled with the microcontroller to handle time and a critical task. So the next one is embedded C programming, the another main part of our internship program. And embedded C programming, for the software we use embedded C. It is a preferred language for such projects because it offers efficiency and portability. It allows us to perform bit level manipulations of hardware registers while maintaining the structure of high level language, which is essential for flash memory and like a RAM 256 bytes. The overview is very simple. The embedded C extension of the C language used to develop software for microcontrollers. It has a bridges gap between high level logic and hardware registers. The key characteristics are hardware abstraction, direct access to the specific functions like TRIS and port and ATCON. Resource management that are RAM 8256 bytes and flash 8 KB of the PIC microcontroller. The very important part of the key characteristics of C programming is infinite execution. Using a while loop on this embedded system, it never stops running on the function while having doing the specific task. The real-time constraints are users interrupts for a time with doing a critical task. Like example, stopping a microwave at the exact second of the time when it hits zero. So the meal didn't spoil on the micro oven. The specific implementation the project. What is the specific implementation projects are data types. Use of unsigned character and unsigned integer to optimize memory. Bit manipulation. Controlling individual pins for the fan, buzzer, and matrix keypad. Header files. Inclusion of hc.h to map C code to the PIC16F877A hardware architecture. So as we previously we saw the C programming, now we is going to see advanced programming concepts that are advanced pointers, macros, and modular programming. So first one, the pointers. What is pointers? It is essential for direct memory manipulation and interfacing with input and output, and also used for memory mapping and passing a large amount of data like LCD strings efficiency without duplicating the memory. So it can stores the memory and do the specific task without duplicating the memory. So we can prevent over memory accesses. Null pointer uses as safety measure concerns to initialize pointers. It ensures the program doesn't access garbage memory. We can prevent it from crashes from the systems in the critical embedded projects. Modular programming. Modular programming is an essential software designed to practice that involves organizing code into smaller reusable code. The structure was very simple. The project was divided into multiple extension files called C and H files, like CLCD.h, CLCD.h, main.c files, etc. The benefits of modern programming is very simple. The reusability. The CLCD driver can be used in any other projects without rewriting. And third one is easier debugging. The issues with the keypad can be fixed in matrix keypad.c without touching the main logic. The third one was macros and embedded C. Macros are powerful texters Macros are the powerful text substitutions processed before your code is actually compiled. Macros that define the code with meaningful names to the hardware pins. So this can make a code readable and easy to change. Efficiency. The macros are handled during pre-compilation to save the CPU cycles during the runtime compared to standard functions. The next one was system architecture. First one is core controller, the PIC16F877A microcontroller. is a 8-bit microcontroller acting as a central processing brain of our project. The user interface is matrix keypad for input and CLCD display for real-time status display. The hardware peripherals are DC fan for heater simulation and buzzer for completion alerts. So now, as an example, if I give a information to the matrix keypad by pressing any keys, it goes to the microcontroller and LCD. The LCD show the function to do on the micro oven. The microcontroller waits for the another input to confirm to do the operation. If again I press one key, the microcontroller confirm the process, and my LCD character shows what the process is going on the micro oven. The micro oven gives instructions to the DC fan. The DC fan enable heat to the micro oven, heats the foods, and when the time is done, the buzzer alerts. So output by the output is coming out by the buzzer. These are the process and block diagram of our project. So next one is PIC16F877A microcontroller architecture overview. In the architecture of the microcontroller, it is a high performance 8-bit RISC CPU with 40 pins CMOS technology, featuring a simplified instruction set for fast execution. The next one is memory and input output ports. Equipped with 8 kilobyte flash memory program and memory above program memory and 368 bytes for the RAM and 5 versatile input output ports to port A to port E for peripheral interfacing. The on-chip peripherals like timer 0, 1 and 2 includes 3 internal timers. These are 10-bit ADC analog to digital converter channels and CCP modules, capture, compare and pulse width modulation used for motor and heater control. We can see about overview. So let us see. The first one is CPU, the Harvard architecture. The CPU uses separate buses for instructions and data, allowing it to fetch and execute simultaneously. The W register, called as working register, is a heart of the CPU used for all arithmetic and logical calculations in our microwave logic. The second one is reset function, that is MCLR. Is an active low pin used to reset the microcontroller in our project. Ensures the system can be restarted in initial stage like home screen if any error occurs. The third one was clock oscillators, OSC1 and OSC2. These pins are connected to the externally crystal oscillator, typically in 20 MHz. This provides a heartbeat or timing frequency required for the CPU to execute code for timers to count accurately. The power supply pins VDD and VSS. VDD pins are 11 and 32, connects to plus 5 volt DC, and VSS is connected to the ground. Both pins pair must be connected to ensure the chip has stable power flow for all interval modules. The peripheral I/O ports, these are A to E. The first one, let us see, is Port A. Port A is an analog to digital converter, features 10-bit ADC channels. These can be used to read analog sensors such as temperature sensor to monitor the heat levels inside the micro oven over the simulation. Port B and D. Port B and D is for high-speed data. It consists of 33 input and output pins and 5 ports. So for LCD display for to transfer high-speed data, and the matrix keypad is for scanning. They provide 8-bit for wide communication. The port C is used for action port for the micro oven simulation. The pin is used to pulse width modulation. You can use this control speed over the DC fan, representing the heater. The port E. Port E is considered as a small 3-bit wide port. Its pins are primarily used as analog inputs or control signals for the parallel save port. In many project use, this port E is used as LCD setups in user to control signals. And the last was And the last is timer to and CCP pins. Timer 2 is an internal 8-bit timer used to create the 1 second delay for our microwave countdown. The CCP pin is used to pulse width modulation to control the speed of the DC pin, representing the heater. So next one. Peripheral interfacing for CLCD, matrix, keypad, and timers IRC. The 4 into 6 character LCD output interference. The LCD display is considered as output interference in our project. Its purpose is acts as primary display for our start menu, cooking the countdown, and temperature alerts. Interference mode is it operation done in 4-bit mode to minimize the number of I/O ports used as used in the microcontroller. The control signals, the RS register select is switch the data between commands and the data enabled to the latch, so the data can display into the display. Those and the next one is matrix keypad, the input interference. Its purpose is used for selecting cooking modes and entering numeric value for the time temperature. The scanning logic of the keypad is uses a row columns or scanning technique where the rows are set as outputs and columns are set as to detect the specific key presses as inputs. Efficiency of the keyboard. Interfacing a 12 keypad using only 7 GPU pins, so the significantly reduced pin count compared to the individual two other switches. Timers and IRC logic. The timer used it as 8-bit timer configured with prescaler for periodic interrupts. And the second one is ISR, known as interrupt server routine, a dedicated function that triggers automatically on timer overflow. The third one was non-blocking countdown. When the ISR is independently track time to the update, the countdown while the main program waits for the user input. The last conclusion and our project outcomes. The comprehensive functionality successfully simulated all 4 operational modes like micro, grill, convection, and quick start, ensuring full adherence to industrial microwave logic. The real-time reliability achieved a highly responsive systems that handles user interrupts and safety stops instantly through precise timer 2 based ISR logic. The hardware optimization. They maximize the efficiency of our microcontrollers' limited resources like 8 KB flash drive and 368 RAM by implementing model embedded C programming and memory efficient data types. Technically proficiency demonstrating integration of complex hardware peripherals including the matrix keepers, LCD displays and etc. include a consecutive event to driven the embedded system. So, thank you, Emertxe Institute of Technology, by giving this opportunity to part of our internship team to learn the embedded systems. And thank you, everyone. And next, we can see about micro oven simulation. Thank you. So now we going to start micro oven project simulation. So let's start with MPLAB. So I already done the project by implementing the code. So and I'm explaining the main code of the source file. The first one is installation configuration, and second, the unsigned character to the power on screen, unsigned character for reset the nothing character when the process is done, extra unsigned character for seconds and minutes. The code starts by calling integer config. This steps configures all the hardware components, the SCDC display, the matrix keypad for input, the matrix keypad for input, and the fan buzzer as outputs. The crucially, it initiates the timer 2 and enables global interrupts like GIE1 to handle the time tracking in the background. In the code, inside the while one loop, the system continuously reads the keypad using read matrix keypad. If the system is on, the menu screen awaits. It waits for the user to select the cooking mode. Pressing key 1, 2, 3, or 4 updates the operational flag to the micro, grill, or convention or start mode respectively. The third from the line in the code. Once the mode is selected, the code enters the switch case depending on the mode. It calls a specific configuration like set.time, the key in the reset flag, or set.temp, set the temperature. These functions allow the user to input the required cooking duration or heating temperatures before the oven actually starts. The real cooking control lines. When the in, Here you see the real cooking lines. When the cooking starts, like display underscore time mode, like display under the time mode. In this mode, it manages the oven state. It checks the key 4 to add 30 seconds to the timer, key 5 to pause the operation like by stopping the fan, and timer 2. Key 6 to stop the cancel and process and to return the menu. Operational state execution. In this operational state execution, by you seeing the switch operational flag or block acts as a state machine for the project. It ensures the correct function is running at the right time. Whether it is displaying the power on message, showing the menu, running faster heater logic via the heat dash food, or handling the pass by stop states by controlling the fan and TMR2 bytes by the code. So let us execute and run this code by enabling clean and build. So you can see the code is now building. So you can see now the code is built and successful. So now we can process the micro oven simulation. Let us go PICSimLab. Now I'm selecting our board, pick Genoise, selecting our microcontroller, PIC16F877A. Sorry, an error occur. Mhm. So now again we select the board, pick Genoise, our microcontroller. So the LCD display size. So now we're going to select. So now the board is ready. So we can going to select the heads file. So load heads. So we already done micro oven sugan.heads production.heads file. So the the micro oven is perfectly working. So powering on micro oven. Uh, Now you can see the 4 modes: micro mode, grill mode, convection mode, and start mode. Now I am selecting micro mode. Uh, Now you can see the power is 900 watt. Um, so now the displayed time set time minutes and seconds. So now I'm going to give a second about 15 seconds. 15. Can you show it? Uh, yeah, okay. I think 6 seconds is enough to do a simulation. So I now am entering. Hmm. So you can see now the micro oven simulation is working perfectly. So now I'm pressing 5 button pass. Come on. Okay. The micro oven is passed. I can start or resume by pressing the 4. So enjoy your meal. The micro oven first mode is done perfectly. So now we're going to second mode, grill mode. Okay, the grill mode is on. I'm giving the same 10 seconds, I think. Okay, okay, 10 seconds enough. Okay, Now again, the grill mode is working perfectly. So now, okay, now I'm going to again restart the button. So it working again perfectly. So time remaining 7, 6. So you can see the temperature by here 27.50 degrees Celsius. So the grill mode is also working perfectly. So third one is convection mode. I'm pressing. So temperature I'm giving, let us give 559. Okay. Okay. Now we enter. Okay. 599 is enough, I think. Okay. Time remaining 60 seconds. Okay, we can wait. Okay. Now we're going to set the time. About, I think, 5 seconds enough. Okay. Sorry. 5 is more. Okay. We can give. Okay. Now it is also working perfectly. Okay. Sorry. Previously I didn't on the buzzer. Now the buzzer also working perfectly. The fourth one is quick mode. Fourth one. Okay. Let us see. Okay. This mode also working perfectly. So now the micro oven perfectly working all the modes. So my project is complete. So once again, thank you everyone, thank you Emertxe Institute of Technology to giving the opportunity and Emertxe staffs to teaching us this course, and thank you to everyone.